Hello everyone, I am Kisina Balkis from Group 5, and in this video, we are going to present our final group project for MAT099. But before we dive in deeper, I'm going to introduce you to my fellow group members, which are Putri Alisha Nabiha, Resha Ristina, Nur Safia, Aina Najiha, and Nabiha Hani Kamilia. In this video, we'll be focusing on task 1, the application of first-order differential equation regarding growth and decay. And over the next 10 minutes, we'll walk you through our data collection process, the step-by-step calculations for our particular solution, and comparison between our mathematical model and real-world results.
This is the population every year from 2004 to 2026. In 2004, the population of Kota was about 773,000. Over the next decades, Kota experienced rapid expansion, surpassing 2 million by 2014. By 2016, the figure reached 2,300,000 and continued rising steadily. In 2020, the population stood at 2,800,000. Although there was a dip in 2021, growth resumes, and by 2025, the population exceeded 3,200,000. In 2026, it remains above 3,100,000.
So now I will present how we model population growth using an exponential function based on the data given. Since the rate of growth is proportional to the number of population, dp over dt equals to kp, we separate the value of p and t and integrate both sides of the equation in order to get the general solution. The general solution can be simplified. P equals to a exponent to the power of kt, where p is the population, a is the initial population, k is growth rate, and t is time in years. So now we take the reference year as 2004, where t equals to 0. Based on the table, we take the population value in 2004 and substitute into the formula the value of p and t in general equation in order to get the value of a. And we got a equals to 773,332. So now our model becomes like this. Next, we need to find the value of k, which is the growth rate. We use another data point from the table. For example, we take 2005 population in 2005 and t equals to 1. Substitute p and t in the equation. So now we solve this equation and let k as a subject. Then take the natural logarithm on both sides. After calculating, we get k equals to 0.0617. So finally, the particular solution become like this. So now let's use this model to make prediction. First, prediction the future population in 2036. So t becomes equals to 32. So the predicted population in 2036 is approximately 6.22 million. Next, prediction 10 years above before 25, which is 2015. So t equals to 11, right? And t we substitute in particular solution. So the estimated population in 2015 is about 1.58 million, which is a bit different compared to the actual value of 2.34 million. In conclusion, the calculated population in 2015 shows a significant deviation from the actual value. It's due to the exponential model assumption of a constant growth rate k, which is cannot account of a rapid increase in population.
This graph shows two sets of data. The orange line represents the actual population data collected from the year 2004 to 2026. The blue dashed line represents the particular solution obtained from the differential equation model. From the graph, we can see that both graphs show an increasing trend, indicating that the population is growing over time. However, the actual population increases more rapidly compared to the model in the earlier years, especially between 2008 and 2015. After that, the model becomes closer to the actual data, showing a better fit in the later years. This difference suggests that the model does not perfectly match the real data, possibly due to the external factors such as migration economic condition or change in birth rate. Overall, the particular solution provides a reasonable approximation of the population growth, but there are some deviation between the model and the actual data.
Now, let's dive into the analysis and discussion of our findings. To determine the precision of our exponential model, we selected the year 2008 as a benchmark to compare the actual population with our calculated estimation. In 2008, the actual population of Qatar was approximately 1,426,938 people. However, our mathematical model predicted a population of only 1,003,640. When we calculate the percentage difference between these two figures, we find a substantial gap. This indicates that while the model captures a general upward trajectory, it significantly underestimated the reality on the ground during this specific period. Moving further down to the timeline 2015, we see an even more pronounced deviation between our model and the actual data. For the year 2015, where t equals to 11, our calculated population falls drastically short of the real numbers. This highlights the core limitation of the mathematical approach we use. Our formula is based on the exponential model, which inherently assumes a constant rate of growth over time. In the real world, population growth is very constant. The model simply cannot account for the explosive, non-linear surge in population that Qatar actually experienced, particularly between the years 2005 and 2010. So, what caused this massive real-world spike that broke our mathematical model? During the mid to late 2000s, Qatar experienced an unprecedented economic boom driven by its liquefied natural gas industry. This triggered massive infrastructure projects and a huge influx of foreign specialized labor and expatriates. Because of mathematical model only looks at past numbers and assumes a smooth, steady percentage increase, it failed to predict the rapid policy and economy-driven population spike. In conclusion, while exponential models are great for idealized scenarios, real-world population spikes require more complex models that account for migration and economic shifts.
To conclude, our team successfully modeled Qatar's growth from 2004 until 2026 by using first-order differential equation. By applying the exponential growth model, we identified a constant growth rate of approximately 0.06517. The strength of this project is its precision. When we tested our model against 2008 actual data, we were off only by 423,298 people, a 29.66% error. This confirms that the exponential model is a reliable tool for Qatar's current demographic trend. Using our particular solution, P equal to 77333 to the power of 0.06517, we predict that the population will reach approximately 3.17 million by 2026. Ultimately, this proves that Qatar's expansion is random, but it is a predictable result because of its geopolitical and economic factors. By mastering these equations, we can better forecast the citizens' needs.